Here's a very important part of this concept of wind shear, and that is that the actual molecules within these bodies of air are moving in different directions. And so let's kind of represent that by just going like this. So the drier air is going to the left, and on the bottom it's going to the right. Now, what do you think is going to happen to these little droplets that are right on that boundary? Well, I know what's going to happen. They're going to start to spin. And as they spin, they're going to elongate into polymers, and they're going to do this in the trillions. As the name suggests, surface tension just means that the molecules on the surface are pulling against each other harder with more force than the molecules below the surface. But let's see what happens when a flawed paradigm tries to make a sensible explanation of this phenomenon. And I found this video, Surface Tension, Adhesion Fluids. It's part of the Khan Academy series, and it's a pretty good series in my opinion. But of course right here they're completely flawed. That's because it's part of a flawed paradigm. Now I'm going to go ahead and show you why their understanding is just nonsense. Completely doesn't make sense at all. And then we're going to go on and explain the correct understanding of what causes surface tension. Let's just go ahead and take a look at this.
It's called cohesion. But what does this have to do with surface tension? Well, the key is...
I cut out the first part of that video. He basically describes this notion of cohesion, the notion that H2O molecules are drawing against each other because of their polarity. And now he's going to try to explain what this has to do with surface, why the surface has greater cohesion than it does below the surface.
These water molecules would like to bunch together. They want to group together if they can. So what would this water molecule do? I mean, which way is he going to go? How does he...
Now note, they show that these water molecules will want to go together with each other. Well, that's really not true. They're not trying to get together. They have very low polarity, so there's hardly any force between them. In this position here, he's showing below the surface. Let's continue with this.
Which one to group with? There's a problem. Here in the bulk of the liquid...
So the forces are all equivalent because it's surrounded. Well, does that happen in solids? Solids are also surrounded. It's a complete nonsense notion. Let's continue here.
And decide, or in other words, let's just say got pulled toward this molecule. Well, it's also getting pulled to the left by all of this. By this one's pulling it back to its original position. This one's pulling it back to its original position because there will be a component of that force that'll point in the direction of its original position.
So he's saying that since the vectors are all pointing in different directions, which is obviously something we have in any kind of a material that has cohesive forces, that therefore there's no cohesive forces. It's literally flipping logic on its head. He's basically telling you this is something that you don't see, when actually it's right there in front of you. And so it's a little bit of kind of a mind trick. This is very common, by the way. Whenever people are put in the position they have to explain something that's nonsense, they're very good at coming up with creative ways of explaining it to where it seems like it makes sense. Let's continue with this.
As well as this one to the left. So these are restricted. These molecules here in the bulk of the liquid have too many other water molecules around them dictating where they need to be, because if they tried to get displaced, it'd pull them back to that position. However, at the surface, there's no water molecules above them. These are freer. They're less restricted. So that allows these water molecules on the surface to group together a little better, form stronger, tighter bonds.
So consider the logic there. The molecules on the surface are less restricted, therefore they're better able to bond with each other. Does that make sense? Does that make sense at all? No, it completely flips logic on its head. Let's continue with this though.
Closer spacing at the surface in such a way that they form a tension that's not present in the bulk of the liquid.
Now, they do form a tension, and they do become closer to each other. Not only that, but there's less movement between them on the surface. So I don't want to harp on this particular presenter. He's doing his best to represent something that's plainly nonsensical. It's not his fault. It's not the Khan Academy's fault. It's because of the fact that we have a confused paradigm, and it all stems back to the fact that we failed to recognize that H2O is a solvent of its own polarity, and only in instances where you can reduce that ability to be a solvent, the ability to erase each other's polarity. Only in those situations do we have surface tension. And so let's go right ahead and let me demonstrate to you exactly what surface tension actually is. Here is, let's say, a representation of water. And now let's go ahead and create a surface in this. So if we remove this one here, we can essentially say that these three are part of a surface. If we think of the surface as running just like that. Now, let's consider all of these molecules having the same situational factors going on here. This one's got something here. This has got something here. And let's say all three of these now only have 3 hydrogen bonds. And so what happens when they only have 3 hydrogen bonds? Well, some of their polarity remains. Look at my fancy graphics here. Some of the polarity remains. And along the surface of the water, the molecules there have higher polarity because they're less surrounded by each other, and therefore they're less affected by the tendency of H2O to neutralize or solve its own polarity, and that's the explanation. Below the surface, they still have 0%. Why? Because below the surface, they're all still surrounded. And this explains why H2O in liquid water is very fluid below the surface. But in situations where you can reduce the amount of hydrogen bonding as occurs naturally on a surface, you get this phenomenon referred to as surface tension. You get this situation where, there we go, where some of the polarity remains. And it's just that simple. There's nothing else to it. There's no reason for all these incredible gymnastics that they go into involving some, well, as we just saw, there's just no reason for that kind of twisted logic to explain this, because now we have a literal understanding of what's going on here, and we're getting away from the superstition that is part of the current paradigm of water. One of the things I'm not comfortable with when it comes to doing what I'm doing here, which is exposing the superstition that's surrounding H2O, is that I'm constantly finding myself in a position of telling somebody that they don't know what they're talking about. And I don't like that. I don't like being in that position. I'm not trying to expose people for having a wrong understanding. That's not my purpose here at all. In fact, I want to bring them up and show that they actually do have some excellent explanations. In fact, the one I'm going to show you here, well, let's go ahead and get to it. This is a video made by, as you can see, his name is Mikkel van Biezen, and it's an excellent explanation of H2O's high heat capacity and its significance. But then it goes on to explain the actual mechanics of it, and that's where they get it wrong. Now, as I will explain further along, the actual cause of H2O high heat capacity has to do with the elastic arrangement that itself is the result of the fact that H2O is a solvent of its own polarity. And therefore, there's an inverse relationship between the comprehensiveness of connectedness and the strength of connectedness. And you're going to hear me say that over and over again because it's very important. But let's first focus on what an excellent explanation Mikkel provides here.
The heat capacity of water is 1 calorie per gram per centigrade degree, or 4,186 joules per kilogram of water per Kelvin. Compared to like metals, that is almost a 10-to-1 ratio. Aluminum has a high heat capacity for metal, but it's only 1/5 the heat capacity of water.
Isn't that interesting? Aluminum only has 1/5 the heat capacity of H2O.
Almost 3/4 of the surface of the Earth is covered by water, and water having that really high heat capacity is able to temper the climate tremendously. If, for example, there was much less water on the Earth, the swings between summer and winter would be enormous, would make it very difficult for life to exist on Earth. And even if there were lots of oceans like there are today, but if the heat capacity of water was only a small fraction of what it is now, then the oceans would heat up tremendously in the summertime and get really cold in the wintertime and freeze over. The large oceans of the Earth really are the thermostats of the world. Now the question is, why does it do so? Why does it have such high heat capacity?
We get to the part that's relevant to what I'm doing here, which is, why does H2O have a high heat capacity. Now, this is where Mikkel fails to provide an adequate explanation of H2O's heat capacity. Keep in mind, he's part of a larger paradigm that has completely failed to understand that H2O is a solvent of its own polarity, and that therefore there's an inverse relationship between the connectedness and strength of connectedness, and therefore that results in something that we've referred to as elasticity. And it is this elasticity that can only be understood by what I'm about to explain, that H2O has a high heat capacity. But let's go ahead and listen to Mikkel's explanation, and then I'll come in and provide the correct understanding.
Well, to try to give you a feel here, you can see that water molecules have a lot of hydrogen bonding. Between every oxygen, there'll be 2 hydrogen bonds with other 2 molecules, and it forms all these structures. Now, when water is in the liquid phase rather than the solid phase, molecules can move from one to the other, but there's still these very strong hydrogen bonds between all the various molecules in 3 dimensions. And so as you're adding heat to water, and so that heat would then cause the molecules to vibrate more violently because of the increase in temperature, a lot of that heat, a lot of that energy that's given to water is actually used to try and break the bonds rather than make the molecules vibrate more. So vibration or kinetic energy is associated with temperature, and the more they vibrate, the higher the temperature. But if a lot of the energy that's dumped into the water is used to break the hydrogen bonds, then less energy then is available to actually cause the molecules to vibrate more. So water can therefore absorb way more heat than other substances. Other substances are much more reactive by increase in heat.
Now, did that explanation really make sense in terms of why water has a greater heat capacity? It really doesn't make any sense. He's just saying that the hydrogen bonds, well, first he said they're strong. Now, as I've described previously, the correct understanding of hydrogen bonds is that they're variable. Their strength actually goes up and down in inverse relationship to their connectedness. That's actually the reason there's a high heat capacity. Now, he's stuck because this understanding that I'm talking about doesn't exist within the current paradigm. And so he's trying to say these 2 molecules have strong bonds between them, and that the energy goes into breaking those bonds, and that's the reason that H2O has a high heat capacity. Considering the limitations of the current paradigm, that's about as good an explanation as one could possibly arrive at. But now I'm going to go ahead and I'm going to explain to you the correct understanding of why H2O has a high heat capacity. And it has to do with the fact that there's an elastic relationship between H2O molecules that itself is a consequence of the fact that H2O is a solvent of its own polarity, and therefore there's this inverse relationship between connectedness and strength of connectedness. I'll repeat that. There's an inverse relationship between comprehensiveness of connectedness, the more they surround each other, and the strength of that connection to each other. That's the inverse relationship I'm discussing here. Elastic relationship, if we think of a rubber band, when you get them apart, the force that's holding it together is even greater. It wants to pull it back. Then when you get them together, there's no longer any force holding them together. And that allows energy to be caught in this situation right here. It's within the substance, there's movement caught within it. And this is the reason why H2O has a high heat capacity. So as H2O molecules move away from each other, they reduce the amount that they neutralize each other's polarity. So as they move away from each other, the force that's keeping them in each other's orbit is greater at some distance. Maybe like over here, it's no longer greater, but right here it's greater, and here it's lesser. And so when H2O molecules completely surround each other, there is no force holding them together, and this produces an elastic relationship. And within that elastic relationship, movement gets trapped. We can think of liquid water as being a whole bunch of these rubber bands. They essentially absorb the movement. And that's what gives H2O its high heat capacity. It's that elastic relationship that itself is a consequence of the fact that H2O is a solvent of its own polarity, and that therefore there's an inverse relationship between its comprehensiveness of connectedness and the strength of that connectedness. And I say it's inverse because the more they're together, the less is the strength. The more you start to pull them apart at some distance, that strength increases. Of course, if you keep going farther, then it's eventually going to break free. But that is the reason that H2O has what we refer to as a high heat capacity. It's the elasticity of hydrogen bonds. It's a very important concept that we need to understand about the elasticity of H2O. The force that's holding them together is not the force that's necessary to pull them apart completely. In fact, it's always going to be at least 25% more. We're going to demonstrate that with two H2O molecules here. On this representation here, they form a hydrogen bond. Now, going by what we've discussed previously, H2O molecules are solvents of 25% of each other's polarity. That would mean that the polarity of both of these H2O molecules in this configuration right here would be 75%. So they both retain 75% of their polarity, but 25% of that polarity has been neutralized by their own proximity to each other, as was discussed previously. Now, from this, you might assume that the force necessary to bring them apart and to turn both of these into molecules of steam would be 75%. But keep in mind what's happening, though, with elasticity is that as you bring them apart, it increases. In fact, it'll increase all the way up to 100%. And as we know, the force necessary to separate molecules into individuals is relatively high at our current pressure. It's at 100 degrees. There's a lot of confusion there when it comes to evaporation, by the way, and this actually has implications on that, but I'm going to get to that a little bit later. But let's go ahead and try to represent the relationship of H2O mathematically. So let's go ahead and do a simple chart here. We have a simple XY graph. Along the bottom here is going to be the distance. That's the distance between H2O molecules, and this is going to be the force. Now, what we would note is that as H2O molecules came together, as the distance got lesser, we're going to see this kind of unusual relationship. At a certain distance, the force starts, and then it's going to build and build and build, and then somewhere around here, it's going to go back down again. Now, of course, we're only talking about the force associated with that 25% here. It would be a much more complex graph if we were talking about each of the relationships with each molecule. It can get extremely complex. But it's important to understand that where the force maximizes is when there's some distance between them. And that has a lot to do with why H2O has such a high boiling point. For the time being, though, let's consider what one of the larger implications of this are. Here's a wider implication of what we just discussed. Let's go ahead and show you that graph again. What if we could somehow, within the body of some bulk water, we could force them to maintain some distance, let's say right around here, so that all the molecules within that were at their maximum force. And we can go ahead and represent that right here. That would be like breaking all of these bonds here, but not breaking them so far that they're not still within each other's influence. As you see here, we break this maybe about one diameter of an oxygen molecule here. And I'm just going to assume, I don't know exactly what distance is involved, I don't think anyone does, but that would be right here. And so now we have a situation where their polarity, each one of these molecules here, their polarity has gone up to 100%, but they're still within each other's sphere of influence. Now, what would result from something like this? Well, one of the things that would result, strangely, is structural properties, and we can demonstrate that vividly through non-Newtonian fluids. So let me go ahead and pull that up. So what I did here is I went to YouTube and I did a search on non-Newtonian fluids. We're going to go ahead and click on this second one here that came up. It's by scienceman.com, And you'll note here in this picture that they show a box of cornstarch, because the typical non-Newtonian fluid that they show us is a combination of cornstarch and water.
Hello, and welcome to another Science Man digital lesson. Today, we're going to take on the interesting topic of Newtonian and non-Newtonian fluids. A classic Newtonian fluid is water. Water has a very predictable viscosity.
It's kind of ironic, or maybe not, that the thing they're showing us here that is a I think they said a Newtonian. Yeah, this is a Newtonian fluid. They're saying water. But we're about to show how a mixture of water and cornstarch is a non-Newtonian fluid. I get those mixed up. It kind of shows you how confusing water can be. But let's, I don't want you to get confused. We want to concentrate on why this non-Newtonian structural properties, why they appear on the scene.
As you can see here, warm honey flows easily, and it will easily flow around objects, such as this ruler. Placing a force on the honey has no effect on its viscosity. Honey, whether it's warm or cold, is a good example of a Newtonian fluid.
So honey is a good example of a Newtonian fluid. It acts in a normal way. Now we're going to try a combination of cornstarch with water.
When you pour this solution, it appears to behave much the same way as the honey. When you place a ruler into it slowly, the fluid flows around the ruler. However, when you attempt to force the ruler into the fluid instantly becomes more viscous.
So they just described that a non-Newtonian fluid will have different viscosity depending on different factors, whereas a Newtonian fluid will have the same viscosity regardless. But note that the difference here is force. And you wonder, well, what's going on? Why is it doing that? Well, I would maintain that the answer to that question is what I've already shown you. The answer to that question is that when you apply force, the starch molecules have enough energy to get between the water molecules and create enough space that it turns on the polarity of the water molecules. And that's the reason. That's the reason non-Newtonian fluids have such incredible viscosity when there's force applied. As soon as as there's a lack of force, we would want to imagine starch molecules being in here when force was applied. But as soon as that's no longer applied, the natural tendency of these things to reform into hydrogen bonds, and it does it instantaneously, returns it to being a very low viscosity fluid. So that's the explanation for non-Newtonian fluids, and it's an explanation that you really cannot arrive at unless you realize that H2O is naturally a solvent of its own polarity, and that situational factors that defeat that ability to be a solvent allow the polarity to reappear, and it does it instantaneously. Now, this phenomenon has completely confounded physics and science up until now. And we're going to go out, and I remember there's some websites where they attempted to explain this phenomenon. I'm going to show you what they came up with. And it's all a consequence of the fact that they just simply didn't, and still don't, understand that simple notion that H2O is the solvent of its own polarity. I want to read one of the comments on here. Well, maybe I should first introduce it's from the University of Chicago. The title is Cornstarch and Water, explained by physicists Heinrich Jaeger and Scott Wojciechowski. And they're dealing with, specifically, as the title indicates, cornstarch and water, so it's a non-Newtonian fluid, and they're investigating the same phenomenon. They're trying to come up with an explanation for it. But let's go ahead and read. This is a comment, and I guess it's the top comment. It's from literally 9 years ago. It says, based on the title, I was expecting to learn about the physics behind it. Instead of hear a physicist say, it's a liquid when you hit it real hard and it turns to a solid. Cool footage nonetheless. So basically, the comment is suggesting that they really didn't explain anything. And I'm going to make the case that they didn't really have a chance of explaining it, because the truth of what's going on there is so completely counterintuitive to anything anyone would consider within physics that there was just no way they could have come to the right conclusion. But let's go ahead and watch this video.
This is something that relates to long-standing question in suspension science, and the issue is, why can you put tremendous stress on these systems without sinking in? These are very, very simple systems, just solids and liquids, fine particles. They behave unlike anything you might expect from an ordinary solid or from ordinary liquid. You see it feels really liquid-like, but then if I pull on it, something new happens, right?
You have water, which is really easy to get, and cornstarch, which we buy for 50 pounds for $20. We actually mix the cornstarch and water together in an industrial cement mixer. So the cool thing is that if you keep it in motion, you can actually handle it for a long time, and then once you put it in, it turns back into the liquid. To actually get the science out of it, you need some really sophisticated equipment. We use high-speed cameras, force sensors, and accelerometers.
As he's indicating there, they're using all this sophisticated technology to figure out what's going on here. Now, if they understood that H2O is a solvent of its own polarity, all of this would have been unnecessary. And so my point is that this notion that I've introduced, that H2O is a solvent of its own polarity, and that therefore when you separate it, you reactivate its polarity, is so foreign to science that it's not even on the radar screen. But let's go ahead and listen to the rest of this video.
One thing we found out, and one question we always had, well, water alone is super weak, and grains alone are also super weak. So why is it that when you mix water and grains together, they suddenly get so strong? Yeah, probably gonna do it right there.
And of course, we know the answer to that. The reason they get strong is because under situational factors where the grains can get between the water molecules, they reactivate the polarity that has been neutralized when they're in the liquid state. That's the correct answer to the question. Now, they never arrive at this correct answer in here.
Well, what we found is that when you strike a dense suspension, what you do is you kind of make a solid object grow out from where you strike it. So you kind of create an iceberg under where the impact occurred.
That's a really interesting comment. He says you kind of create an iceberg under where the impact occurred. And that's actually pretty accurate. Ice is a situation where H2O molecules are disassociated from each other. I know that sounds strange because the current paradigm says something very different, but ice actually is a situation where bonds have been broken within it to thus allow for this hard phase to exist. And he's correctly deduced that, but not really on purpose, just kind of by accident.
And so what that means is that even though you're striking a small area, you're making a ton of fluid, a ton of suspension move.
What happens is you transform a liquid by a process called jamming temporarily into a solid.
Most things, you would think if I hit it really hard, I'm going to break it. This is a fluid normally, and if I hit it hard, it turns it into a solid.
So I've already read one of the comments, but there's another comment here I want to read. It's from a person whose name is, let me see, it's down here somewhere. There it is right there. A person whose name is James McGinn. Yes, that's me. This was 4 years ago, and it's actually a little bit of a long message. I'll just go ahead and paraphrase it. H2O has surface tension. It's literally a hard phase of H2O. As the name suggests, surface tension occurs on the surface of liquid water. So think about that. A solid exists on the surface of water. Now consider, what if you had some way of creating a surface within the liquid in 3 dimensions? And then I said, this is the correct explanation of the phenomenon. It's surface tension that exists in 3 dimensions. And then I says, by the way, this understanding provides an alternate hypothesis for ice, which is currently misthought to be a result of lattice. This new understanding suggests the lattice hypothesis is mistaken. And then I go on to indicate that I'm a scientist, that I'm not just a person responding here. And I got 1 thumbs up on here, but here's the thing. That 1 thumbs up, I'm pretty sure, if I remember, came from me. So I got no approval from anybody else from that comment, but I did get 1 response. Let me go ahead and read that response to you right now. It's from Michael van der Nold, and here's his response. And it turns out he's actually correct, by the way. Everyone who studies dense suspensions will tell you that your explanation is wrong. So everyone knows that I'm wrong. So and I've gotten very used to that attitude from people, but there is just no doubt that what I'm saying is the correct understanding, because the current understanding they have is just nonsense. And we live in a world where this notion that H2O can be a solvent of its own polarity is just non-existent. So one of the realizations that comes from the fact that H2O is a solvent of its own polarity is that there is this inverse relationship between the connectedness of H2O to the strength of connectedness. Now, it's important to understand, though, when we're talking about connectedness with H2O, we're talking about something that's very relative. So, for example, here in this configuration, which we showed was really the kind of configuration you have when you have non-Newtonian fluids, they don't really, well, I'm not showing you the right screen here. Let me get to the right screen. And so we started out here. And so when we are dealing with something like non-Newtonian fluids and we put space between the molecules, they don't really appear to be connected, but we're really saying they are connected. And they are, because there's still enough force between them that's holding them together. And in conjunction with the cornstarch, it creates a solid substance. But what if, for the time being, we're only going to look at H2O when it's actually connected to each other and try to come up with some rules as to what type of stability we can get out of it. So, for example, under this configuration, they're highly connected, but the force of that connectedness, as we discussed previously, was very low. And then we noticed that when we pull one off, we now, and essentially we have a surface right there. And these molecules along that surface all have 25% polarity. Now, let's say, though, that we wanted to go even further. Let's say we just had two H2O molecules. There's a lot of force connecting them because they're both at 75%. But in terms of structural significance, the structural significance is very low. So we can ask ourselves the question, where does structural significance exist within H2O? We know that when they're almost completely isolated from each other, it's very low. We also know that when they're connected to each other, it's literally non-existent, as in liquid water, and that when we do create a surface, there is some structural significance, but it's only along the surface, and that when we do create, as happens in non-Newtonian fluids, and we do have structural significance, but one of the things about non-Newtonian fluids is that structural significance disappears just as soon as these things come back together again. So it's a very brief structural significance. What if we wanted to understand what situational factors might allow it to have kind of a consistent structural significance, and we only looked at that? When you have two connections, that's where you have the greatest combination of strength of connectedness and comprehensiveness of connectedness. When you have four, you get too much connectedness, and that lowers the strength of connectedness. And where you have 1 to 0, you have greatest strength of connectedness, but the actual degree of connectedness itself is very low. And so therefore you don't have structure. Structure takes place in the sweet spot between the strength of connectedness and degree of connectedness, which is around 2, which just happens to be a polymer. So within H2O, there's actually a hidden structural capability that's associated with its ability to be a polymer. But how can H2O maintain its polymerization? How can it keep from, let's say, folding over on itself, or other molecules coming in here and weakening the structure by lowering the polarity? We would expect then in nature that there should be situational factors where this can happen, and it turns out there are. Here's a video I found. It's by an organization called Socratica. It's an excellent presentation. And here, this presenter, she's talking about how water molecules adhere.
A closely related property is water's ability to adhere to surfaces, again, by forming hydrogen bonds. Adhesion allows water to crawl along surfaces. For instance, how water grabs onto the walls of xylem tubes in plants. Cohesive nature of water and its adhesion to the side of tubes allows water to be pulled up through plants in a process called transpiration. Think of giant redwoods that can grow hundreds of feet tall.
Does adhesion really describe how H2O is able to make it up to the top of these really tall trees? There's actually a problem with this. And the problem was made very explicit in another video that I'm going to show you right now. This is a video entitled Why Trees Are Out to Get You. It's by Veritasium. It involves Derek addressing some of the issues that come up when we try to make sense out of this notion.
There is a limit to the height that water can be sucked up a tube. It's 10 meters. For a tree to raise water 100 meters, it would have to create a pressure difference of 10 atmospheres. How would trees do that? When I posed this conundrum, a lot of people said the answer is transpiration. But in a liquid, you can go lower than zero pressure.
He's actually coming to the right conclusion with respect to the analogy of a vacuum. He's saying this can go beyond a vacuum. But really what he's saying is there's tension between the molecules. In other words, H2O can act like a polymer.
And actually get negative pressures. In a solid, we would think of this as tension.
There's really a very simple explanation of how these polymers are able to get to the top of the tree. As the wind blows, the trees bend a little bit, and as they bend, that tube lengthens. Water is being pulled up like a rope to the top of the tree. Now, he's discussing it, though, in terms of atmospheres because that's the context. The notion that H2O could literally be a rope going from the top of the tree to the bottom of the tree is too amazing for people to actually imagine. What is maybe the most completely confused notion in all of science is the nature of evaporation of H2O. Most of us, when we are children, we assume when we notice water disappears, when it's left out in the room, we assume it turns gaseous. Now, let's say though that you actually looked at an H2O phase diagram and you noticed that the boiling point of H2O is much higher than will supposedly allow it to become gaseous. Now, we would assume if someone noticed that they would say, oh, well, therefore, H2O, when it evaporates, it doesn't become gaseous. It actually remains, to some degree anyways, in a liquid state. That's actually what is the case. H2O, when it evaporates, it actually still remains. In other words, they're still connected to each other to some degree. It only evaporates as very small droplets, sometimes nanodroplets. Now, that is unfortunately an extremely controversial notion because much of science has resigned itself to the notion that when H2O evaporates, it becomes gaseous. The reasoning for that is that people would assume that if it did remain liquid, that you'd at least be able to see it. And that's a bad assumption. Everyone knows that there's liquid water in the air to some degree. We can all see clouds, and we know that clouds are made up of very small droplets. That's completely not controversial. But people assume that, therefore, when you see clear moist air, that it must have individual molecules of H2O mixed into it rather than droplets. The reality is it has extremely small droplets of H2O. Now, before there was this understanding that I'm introducing here, that H2O is a solvent of its own polarity, and that therefore there's this inverse relationship between the strength of its connectedness and the comprehensiveness of its connectedness, it would have been very difficult to explain to people why it is that H2O wouldn't be apparent, why you wouldn't see the fog coming out of water as it evaporates. And you can kind of ask that as a rhetorical question to yourself right now. Why do you not see fog coming out of it? Well, the answer is because H2O is a solvent of its own polarity, it can form extremely small droplets, extremely small. We're talking all the way down to 10 molecules. My guess it's probably closer to 25 or even 100. The warmer it is and the higher the pressure, the greater the force of air molecules slamming into these water droplets that are floating around in the atmosphere. And the more they do that, the more they split them into smaller droplets, the more invisible they become. And also, interesting enough, the more kind of inert they become. They become like little pieces of dirt, in a sense. very small, very hard, not very liquidy, because they're mostly surface tension. And because of this, because of all these factors, it seems extremely counterintuitive to us that there could ever be liquid H2O in the air. But the reality is there's never anything but liquid H2O. And that is if you stick with this strict definition of a liquid as being, more than two molecules. Now, if you wanted to define some H2O as, say, below 25 molecules in a nanodroplet as being neither liquid nor gas, then you could make that argument that there is this non-liquid form of H2O in the atmosphere. But the point is that at no time in Earth's atmosphere, at the temperatures in which we exist, is it even remotely possible for H2O to be gaseous. That's a complete impossibility, and all you got to do is take a look at the H2O phase diagram, and this will be obvious to you, but that doesn't mean you're going to defeat your willingness to believe something that you've believed all your life, that when H2O is invisible as it evaporates, that it becomes gaseous. Again, it's completely impossible for it to be gaseous. But most people have gone their whole life believing it becomes gaseous, and so they're just going to continue doing that. Now, if you wanted to make arguments to the effect that H2O must be gaseous when it's invisible in the air, well, you're welcome to it. But what you'll find is that the subject is so perfectly confused that you'll have a very difficult time coming to a concise answer on the subject. And here's the worst part about it all. All of science believes like we did when we were a child. They haven't advanced beyond the point of believing that when H2O disappears, that it becomes gaseous. And when I say all of science, I'm talking about all of science. It even goes as far back as Newton. Newton assumed that, and because most of us follow in Newton's footsteps and other scientists' footsteps, and they all kind of follow in Newton's footsteps, everybody believes something that is really nonsense. There is no gaseous H2O in Earth's atmosphere. Now, this creates some issues because one of the notions that's popular among meteorologists is that the weight, the density, determines whether something can go up or down. That, too, is very oversimplified. And so, therefore, they assume that if H2O maintains a density, any kind of density at all, that it's going to start to fall in the atmosphere. And it just simply isn't the case. H2O is greatly attracted to static forces in the atmosphere, and there's no shortage of static forces, electrostatic forces, I should say, in the atmosphere. And so there's plenty of liquid H2O in Earth's atmosphere. It's not in any way controversial that water could remain up. There's also a lot more energy in the atmosphere than people realize. Air molecules are slamming into each other, into us, and into any water molecules in the atmosphere at hundreds of miles an hour. We don't notice this because we're at the same temperature and we're essentially hitting back at the same, our body has the same movement going on with it, and likewise with the other molecules in the atmosphere. But the reality is that the fact that there's moisture that rises in the atmosphere has little to do with gravity and with weight. That's extremely overwrought. It's an extremely simplistic notion to suggest that the weight controls whether something goes up or down in the atmosphere, as if that's the only factor involved. But all of this stuff was adopted from back in a time when we just went with whatever Newton believed. Newton believed that weight controlled everything that goes up or down in the atmosphere. We kind of just step our way back in our mind to arrive at that conclusion. And unfortunately, this has inundated many parts of science, especially meteorology. This is a little video I found called Static Electricity and Water. It's by an organization called Jefferson Labs.
So when I fill it with water, it leaks out of the bottom.
If I charge the pipe, the water is attracted to it. That's because water molecules are polar molecules.
Two hydrogen atoms are bunched up on one side of the oxygen atom that have an asymmetrical distribution of charge are called polar molecules.
Now, as they describe, if there's any kind of a charge at all, H2O is going to be attracted to it. And guess what? It doesn't matter whether it's negative or positive, and they're about to demonstrate that right here.
Let's say the pipe has a negative electrical charge. If I bring it close to the stream of water, the water molecule flips so that the positive end is pointed towards the negatively charged pipe.
So it doesn't matter whether the charge is negative or positive. Any charge at all will attract H2O molecules, and Earth's atmosphere is always got one kind of a charge or another. There is another reason why traditional meteorology has assumed that the H2O that's in clear moist air is gaseous, and that is because without the assumption, there's no way in the world moist air could be light enough to rush up and cause storms through a process that we refer to as convection. Now in another video, I worked out the math on that, and it came to a 1% difference if we assume that the molecules in the air actually could become gaseous. As I've explained already, it's completely impossible for H2O to ever become gaseous, and therefore, no matter how you do the math, moist air in Earth's atmosphere is always going to be heavier than drier air. And therefore, this notion there's such thing as moist air convection that causes storms is complete nonsense. This, of course, opens the door to the question then, what does cause the uplift in Earth's atmosphere? As I've explained in other video, the actual process of flow in Earth's atmosphere involves tubes, and these tubes are vortices. And vortices are literally structural entities that emerge in the atmosphere, and they emerge on wind shear boundaries. And after they emerge, they can effectuate the transfer of air, shooting it into the jet stream. And that this, what I refer to as the plumbing of the atmosphere, is what allows for there to be storms and what causes the uplift in the atmosphere that has previously been attributed to convection. Now, this notion creates a conceptual problem for my model, and that is for these tubes to actually work, to actually be able to suck air from one place and shoot it into the jet stream, these tubes must have some kind of structural capability. And as you can imagine, I have an explanation for that, and it's actually what I've been leading up to in this whole segment here. So let's get right to that. There are boundaries in the atmosphere between bodies of moist air and bodies of drier air. One of the phenomena that happens along the boundaries between where they kind of connect to each other is this concept called wind shear. Let me go ahead and show you what we mean by wind shear. So let's say we have two bodies of air here, and there's the boundary between them. Now, almost always the drier air is higher, and then we have the moist air. These are the molecules of air, like this. Now, both of these bodies of air have some degree of moisture in them, but the droplets in the moist air are going to be larger and they're going to be more plentiful. And also, here's a very important part of this concept of wind shear, and that is that the actual molecules within these bodies of air are moving in different directions. And so let's kind of represent that by just going like this. So the drier air is going to the left, and on the bottom it's going to the right. Now, what do you think is going to happen to these little droplets that are right on that boundary? Well, I know what's going to happen. They're going to start to spin. And as they spin, they're going to elongate into polymers, and they're going to do this in the trillions. This water gets spun up. Polarity is now at 50%, and now all these spinning micro droplets are more attracted to each other, and they start to churn together, and they start to form kind of a plasma. Now, this plasma is what allows vortices to exist. Does that sound ridiculous? Well, I suppose it does, but it's the only way we can explain this phenomenon of a vortice. I realized a long time ago that vortices had to have structural properties. I say that because there's a number of instances where there's phenomena which clearly indicate that vortices do have structural capabilities. So this is really what's happening in the atmosphere. It just happens to be the way our atmosphere actually operates. It actually operates because of vortices. You see, our atmosphere, there's all this disbursement and friction among the gases, and they don't flow well. When you have dry air and you have no structure, there's a tendency for any energy that gets put into it to just get spread out. Now, for there to be a fast type of flow, there has to be some way for the energy of that flow to be conserved, to not just disperse. And the only way to do that is if you have some kind of a structure that provides a passage or some kind of a tube. And that's what happens on wind shear boundaries. A type of water-based plasma comes spinning out. Now, if not for the fact that H2O has this ability to polymerize, this phenomenon couldn't happen, because only when they go into the polymer state do they have the leverage they need to be able to take advantage of wind shear to spin faster and faster. And what eventually happens is they spin really fast, their polarity increases, they start to bang against each other, and they break into smaller pieces, which causes the polarity to go up again. So when you see a tornado, you're seeing a phenomenon that is actually a tube. It's actually a tube that has structural properties. 9 times animals rain down from the sky. I'm going to go ahead and click on that.
Join me while I look at some times that it literally rained animals. Unlike some of the other animals on my list, there are many reasons and many possibilities for these things to rain down from above and from afar. Intense winds can literally pick them up and fling them around with no effort. Then, of course, you have things like tornadoes and waterspouts, which can also shoot them up into the atmosphere until they then come raining back down, not unlike the fish in Australia.
Now, if you think about that, how can animals rain down from the sky if there's really no structure to anything that's pulling it up there? When I was very young, I got this book on meteorology, and within one of the blurbs, one of the side things, they talked about this phenomenon where sometimes fish and frogs and other stuff that comes from a pond, let's say, or that comes from even from the ocean, falls out of the sky. Now, it's important to understand something. It doesn't just fall out of the sky in the vicinity of the pond or the stream from which it originated. No, it gets picked up and it gets carried for miles. And it all tends to get dumped in the same vicinity. So there's no way anything in the atmosphere can do that if it doesn't have structural properties. Now, this phenomenon has been known for a long time, and you can confront meteorologists about it and ask them, well, why does this happen? And why are you not investigating the fact that therefore there must be some structural properties in the sky? And they'll just shrug their shoulders and tell you that they know what they're talking about, and you'll never get anywhere with them because they're completely delusional. They're delusionally lost into their own belief that they understand something that they don't. The uplift that happens in storms is completely caused by vortex activity at higher altitude. It has nothing at all to do with convection. There's no such thing as moist air convecting or being lighter than dry air. Moist air is always heavier than drier air, so there is no buoyancy of any air over other air, and that's not really the way the atmosphere works anyways. What there is, though, is these tubes, and we've seen these tubes in tornadoes. Now, the notion that these tubes could have structural properties is so outside the realm of what people will consider, but again, it comes back around to the fact that we are completely confused and bamboozled by water. That's where the problem is. Now, as I've explained in earlier parts of this video here, structural properties definitely a part of what's going on with water. I mentioned this right here. We have this 0 to 4. That's the number of connections. And this is the strength or the polarity. And as we can see, is if you can get it down to 2, which happens in a polymer, you have structural properties right there. Wind shear is what causes the droplets therein to begin spinning. Once they begin spinning, they elongate into polymers. These polymers now have greater structural capability, and they start to collectivize. They're attracted to each other. And of course, they're also going to exist mostly where there's flow, and they're going to actually surround the flow. And in so doing, they create a pipe that has the ability to conserve the energy of the flow. And that's what's happening with vortices in the atmosphere, and that's why we have this phenomenon that's very closely associated with storms. The next section is going to deal with ice. And you're going to see that just like the things we've been discussing so far, when you understand H2O is a solvent of its own polarity, and that therefore there's an inverse relationship between the connectedness of H2O and the strength of connectedness, that we now have the tools with which we can actually understand what's actually happening in ice and get beyond the superstition that has essentially made a mess of what we currently understand about ice. One of the notions that we're going to use as kind of like a litmus test of whether or not we actually understand what we're talking about is that I'm going to explain super chilled water, which is something that hasn't been explained by science before. And so that's my promise to you in part 3 of this video series, the most devastatingly subtle misconception in the whole dang history of science. We're going to solve super chilled water.